Hi, good day. So let's have an example for the influence line for a truss. For the bridge truss shown below, draw the influence line for the letter A, vertical reaction at A, letter B, the axial load on member FG, and letter C, the axial load on member CF. So for this given truss, let's have the first requirement, that is the vertical reaction at A. So let us assume that we have this vertical reaction at A. Let's say this is R sub A, and the vertical reaction at E, let's say this is R sub E. To represent the moving loads, so we are to place a 1 unit load on the deck of this bridge truss. Let's say that is 1 unit load at a distance of, let's say at a distance x from point A. Since the distance between the supports is 12 meters, the remaining distance will be 12 minus x. That is from the 1 unit load to point E. Alright, so let's have the equation for the vertical reaction at A. So we may do, this is the summation of moments at E equal to 0, assuming clockwise moments to be positive. So that will be the vertical reaction at A. This is R sub A multiplied by 12 meters minus that 1 unit load multiplied by its distance from point E is 12 minus x equal to 0. So we'll be having the equivalent of R sub A will be 12 minus x all over 12. Or we can have the equivalent of R sub A is equal to, this is 1 minus the x over 12. So this will be the equation of the vertical reaction of at A. For the interval that is from 0 is less than or equal to x, less than or equal to 12 meters. Then for example, how about the vertical reaction at E? Since we have now the value of R sub A, we can do a summation of forces vertical equal to 0. That will be, we have R sub A plus the R sub E minus 1 is now equal to 0. So we have the equivalent of R sub A, that is 1 minus the x over 12, then plus R sub E minus 1 is equal to 0. So we have the equivalent of the vertical reaction at E is now equal to, we can eliminate this term, so 1 minus 1, transpose x over 12, negative x over 12, that will give us a positive value of x over 12. So this is the vertical reaction at E. So the same for a span of, or for the interval from 0 to 12. Okay, so since we are looking for, or we are required to draw the influence line for R sub A, so we are to use the values of x. Let's say I'll be using the exact values, that is for the points A, B, C, D, and E. Those are the joints on the deck of this bridge truss. For the corresponding values of x, what will be the equivalent value or the ordinates of the influence line for the reaction at A if we have R sub A equal to 1 minus x over 12. So we have those values of x as 0, 3, 6, 9, and 12. So I'll be using the mode table of our calculator. That's number 7. So for the function 1 minus, let's say that is alpha x over 12. So for the start is 0, and will be 12, and step is, our step is every 3 meters. So that is, we have at x is equal to 0, the value of RA is 1. At x is equal to 3, the value of x is 0.75. At x is equal to 6, the value of R sub A is 0.5. Then at x is equal to 9, the value of R sub A is 0.25. Then at x is equal to 12, the value of R sub A is 0. So these are the ordinates of the influence line diagram for the reaction of A. If we are to draw this one, so we have that at x is equal to 0, we have the value of the ILD for RA is 1. Then at x is equal to 3, that is 0.75. At x equal to C, or at x equal to 6, that is 0.5. At x equal to 3, that is 0.25. Then at x equal to 12, that will be 0. So the appearance of the influence line diagram for the reaction at A will be this one. So we have the ordinates, that is 1, 0.75, 0.5, and 0.25. So this is the influence line diagram. Let's say this is the ILD for the vertical reaction at A. So that will be for the first requirement. So let's try letter B. The axial force on member FG. As you can see for this truss, member FG is a top chord and let's say somehow far from the support. So we may use the method of sections. So let's say we are cutting the members FG, CF, and CD. We cut and expose, then assume that the axial force in each member of those cut members will be under tension. Okay, so let's say these are the free body diagrams of the cut sections. So let's say this is the left side and this one is the right side. Okay, so we have the equivalent of the reactions, vertical reactions earlier, that is the R sub A, the 1 minus x over 12, and R sub E, that is the x over 12. Okay, so let's have the equations for the equivalent of the axial force for member FG. And first, we are to assume the location of the 1 unit load that represents the moving loads. So for example, I'll be assuming that we have this 1 unit load on the left side. Let's say this is the 1 unit load. How do we represent the equivalent of the axial force for member FG? So if we are to have an equation of equilibrium, so sometimes it is more difficult to express the equation of this unknown. For a reason, we have this 1 unit load at a variable distance from A at a distance of x. So if we have this 1 unit load, on this side, we assume that the interval is at an interval that is 0 is less than or equal to x, less than or equal to 6. Or simply, that is from point A to point C. So to avoid this 1 unit load, we may simply analyze the other side. Okay? To have a more simple analysis, we are avoiding this 1 unit load. So again, this is for the location of the 1 unit load. For the interval 0 is less than or equal to x, less than or equal to 6. So again, why is it that this is our interval, but we are analyzing the right side? Take note that this interval represents the location of the 1 unit load. Okay, so we have this free body diagram. The distance from point C to point D is also equal to 3 meters. How do we represent the equivalent of the axial force for member FG? So if we are to extend this member CF and CD, their common point is point C. So we can have the equivalent of the axial force for member FG by doing summation of moments at point C equal to 0, assuming clockwise moments to be positive. So both are counterclockwise, FGN, the RE. There is a negative FG. This is multiplied by 4 meters minus, that is the R sub E, that is at a distance of 6 meters from point C equal to 0. So we'll be having the equivalent of the axial force for member FG as negative R sub E, or the reaction at E, times 6. This is divided by 4. So we'll be having Okay, the axial force for member FG, okay, what is the equivalent of RE? The RE is equal to X, okay, over 12. This is multiplied by 6, okay, divided by 4. So we have the axial force for member FG, that is 6 over 12 is 1 half. Okay, so 2 times 4 on the denominator will be, okay, this is supposedly negative, okay, negative X over, this is negative X over 8. So that is the equivalent of the axial force for member FG, okay, negative X over 8 for the interval 0 is less than or equal to X, less than or equal to 6. Okay, then for example, if the 1 unit load is already on this interval, okay, starting from point D, let's say from point D to point E. So we are removing the 1 unit load on the left side. Okay, how do we express the equivalent of the axial force for member FG? So if the 1 unit load is already on the right side, we may use the left side for a more simple analysis. Since again, we are avoiding the one unit load. So if the 1 unit load is on the right side of the cut sections, okay, so we are considering the interval starting from point D. Okay, point D is at 9 meters. So the interval is at 9 meters is less than or equal to X, less than or equal to 12. But again, we are considering this section, the left section, since again, we are avoiding the 1 unit load. So if the 1 unit load is now at the interval 9 is less than or equal to X, or less than or equal to 12, let's have the equation of the axial force for member FG. We may do summation of moments at point C equal to 0, assuming clockwise moments to be positive. Just to eliminate these unknowns, CF and CD, we are doing the summation of moments about point C. So that is the same as R sub A. This is the reaction at A times 6 plus the axial force for member FG. This is multiplied by the height of this post is 4. This is times 4 equal to 0. So we'll be having the equivalent of the axial force for member FG is equal to the reaction at A. This is times 6, okay, divided by 4. And again, it is negative since we are to transpose. Now we are to substitute the equivalent of RA, or that's the vertical reaction at A. The equivalent of the axial force for FG is equal to, we have R sub A is 1 minus X over 12. This is multiplied by 6, okay, divided by 4. And again, this is supposedly negative. We have the axial force for member FG is negative. That is 6 over 4. That is 3 over 2. So negative, this is negative 3 over 2. Then negative times negative will be positive. 6 over 12 is 1 half. Then again, 2 times 4 on the denominator. That will be X over 8. So this will be the equation of the axial force for member FG for the interval 9 is less than or equal to X, less than or equal to 12. So let's have the ordinates of the ILD for the axial force for member FG considering these two equations. So for the interval, that is from 0 to 6, that is f sub g is equal to negative x over 8. Then for the interval 9 to 12, that is f sub g equal to negative 3 over 2 plus x over 8. So we have again our interval and our equation. So let's have the mode table again for this calculator. Let's say this is mode number 7. So for our first interval, that is from 0 to 6, our equation is negative x over 8. So I'll be using the values for x. Let's say this is from 0, that is at A, then B, that is at 3, then we have at C, that is 6. So equals, we are starting at 0, we are ending at 6, and the step is every 3 meters. So we have at x equal to 0, that is obviously 0. At x equal to 3, we have that as negative 0.375. Then at x equal to 6, that will be equal to negative 0.75. This will be the ordinates for the ILD, for FG. For that interval, from 0 to 6. Then for the next interval, that is after the cut sections, so let's have our equation. So our equation this time is negative 3 over 2, then plus, that is x over 8. Then we are starting at 9, ending at 12, and the step is every 3 meters. So we have that as negative 0.375 and 0. That is at x is equal to 9, and at x equal to 12, this is negative 0.375. And we have at x equal to 12, that is 0. So these are the ordinates for the ILD, for the axial force for member FG. So let's plot them for the ILD. So we have at x is equal to 0, that is also 0. So this is for, let's say, the influence line diagram for the axial force for member FG. At x equal to 0, that is also 0. At x is equal to 3, that is negative 0.375. This is negative 0.375. Then at x is equal to 6, that is equal to, let's have it as negative 0.75. Then we go to the other interval, that is from 9 to 12. At x is equal to 9, it is again negative 0.375. Then at x is equal to 12, that will be equal to 0. So as you can see, this will be our the influence line for the axial force for member member FG. So as you can see, we have all ordinates are negative. So we have all the ordinates of the influence line diagram for the axial force for member FG are negative for a reason. Again, if you are to recall, member FG is a top chord. For top chords, for a given truss, most of the time, or for example, we have vertical loadings, they are compression members. So for top chords, they are compression members. So if they are compression members, we'll be having a negative axial force, or that is a compressive axial force. So this is the equivalent ILD, or the influence line diagram for the axial force for member FG. So for letter C, the axial force on member CF. So since member CF is one of those cut sections earlier, so we are to separate again the left side and D. This one is the right side, and including the support reactions. We have the RA and the R sub E. So we have member CF is an intermediate member, so it can be sometimes it is under tension or sometimes it is under compression. And it's let's say its slope, it is a 3 horizontal, 4 vertical. So let us assume the location of the 1 unit load. and our interval, let's say if the 1 unit load is somewhere between points A and C, this is 1 unit load, we are considering the interval that is from 0 is less than or equal to x, less than or equal to 6 meters. So if we are to consider vertical forces, okay, we can disregard C, D, and F, G since they are horizontal. Okay, for this case, we may include or we may not avoid the 1 unit load. Okay, so we can have summation of forces vertical equal to 0, assuming upward forces to be positive. That is the R sub A, plus the vertical component of CF, that is 4 over 5 of the axial force for member CF minus the 1 unit load is equal to 0. The equivalent of RA is 1 minus x over 12. And then this is plus 4 over 5 of the axial force for member CF minus 1 is now equal to 0. And then we can have the equivalent of the axial force for member CF. And that is equal to, we may eliminate these terms. 1 minus 1 is 0. Then that will be, the equivalent of CF will be, this is 5 over 4. Multiplied by the x over 12. And that will be, I think that will be positive. So we have the equivalent of CF is now 5. 4 times 12 is 48 of x. So this is the equivalent of the axial force for member CF for the interval from 0 is less than or equal to x, less than or equal to 6. So our next assumption is that what if the 1 unit load is already on this side of the cut section. So we have on the right side, that is the 1 unit load. So how do we compute for the equivalent of CF? So we'll be removing the 1 unit load on the left side. Can we still use this? This one? Yes, we can still use the left side this time. If we are to do the summation of forces, summation of forces vertical equal to 0, assuming upward forces to be positive, considering our interval this time, the location of the 1 unit load is already on the interval of 9 is less than or equal to x, less than or equal to 12. Or you can also use this right side. But I'll be using the left side this time. So that is simply R sub A plus the vertical component of CF, that is 4 over 5 of CF equal to 0. So those are the two forces, vertical forces for this side on the left side. R sub A is, that is 1 minus x over 12 plus the 4 over 5 of CF equal to 0. The equivalent of CF is now equal to, if we are to transpose, that is the same as negative 5 over 4. Then, that will be positive this time, plus 5 over 48 of x. Okay, so this will be the equivalent of CF. Yes, that is 4 over 5 times this one. That's negative 5 over 4. Then 5, that is 5 over 48 of x. So this is the equivalent of the axial force for member CF. For the interval, for this interval, 9 is less than or equal to x, less than or equal to 12. Actually, we can also use this left side. I think we will be arriving with the same equation. So since the 1 unit load is already on this interval, the 9 is less than or equal to x, less than or equal to 12, then we do the summation of forces vertical equal to 0. That is x over 12 minus this CF, its vertical component is, again, that is 4 over 5, since that is a 3-4-5 slope. That is 4 over 5 of the axial force for member CF minus the 1 unit load is now equal to 0. So if we are to compute for the equivalent of the axial force for member CF, that is equal to, that is x over 12 minus 1 to be multiplied by the 5 over 4. So we have CF is now equal to 5 over 4 times negative 1 is negative 5 over 4. Then 5 over 4 times x over 12, that is plus 5 over 48 of x. So as you can see, we arrive with the same equivalent of CF, considering the left side and the right side of our free body diagrams. So let's have the ordinates. The ordinates of the ILD for the axial force for member CF. So this is for the interval 0 to 6. That is 5 over 48 of x. That is CF is equal to 5 over 48 of x. For the interval 0 to 6. Then the other equation, that is negative 5 over 4 plus 5 over 48 of x. For the interval 9 to 12. So we have that as CF is equal to negative 5 over 4 plus 5 over 48 of x. So let's have the ordinates. Again, using mode table. So that is the same as mode number 7. So our first equation is simply 5 over 48 of x. Then we are starting at 0, ending at 6. And the step is every 3 meters. So we have at x equal to 0, the value of the ordinate will be 0. At x equal to 3, that is positive 0.3125. Then at x equal to 6, that is equal to positive 0.625. So these are the ordinates of the ILD for the spans or for the interval 0 to 6. Then for the next interval, that is from 9 to 12, so that is, we have our equation. That is, we are putting a negative, this is negative 5 over 4, or we can just restart. Negative 5 over 4, plus the 5 over 48 of x. We are starting at 9, ending at 12, and the step is every 3 meters. So at 9, it is negative. That's negative 0.392. This is negative 0.31 or 3125, I think. Then at x equal to 12, that will be 0. Okay, so if you are to plot these values, let's say this is the influence line. The influence line diagram for the axial force for member CF. So at x is equal to 0, that is also 0. At x is equal to 3, that is equal to positive, that's positive 0.3125. It's positive 0.3125. At x is equal to 6, that is equal to positive 0.625. So which means, if we have the moving load from the interval 0 to 6, we'll be having the axial force for member CF will be under tension. Since we have positive ordinates for the influence line. But if we are now to proceed on the second interval, that is from 9 to 12, we will be having an ordinate of negative. This is negative 3125. Then at x is equal to 12, that will be 0. Or maybe we are to use the same color pen. So this is negative 0.3125, then 0. So we may connect this one. This is the Okay, we may say this is the transition interval from 6 to 9. The axial force started to change from compression to from tension to compression. Okay. Okay, so this will be the equivalent ILD, or the influence line diagram for the axial force for member CF. So this will be our solution for this example.